Struggling with AI model-serving system design interviews? Let's design a high-performance AI model-serving platform.
Ever wondered how OpenAI and Anthropic serve massive AI models like GPT-4? The infrastructure needed for low-latency inference at scale is often underestimated. What if you could achieve sub-50 megabytes latency and 1,000 plus QPS, a 20x improvement? By the end of this video, you'll learn how to design an AI model serving platform, handling workloads like vLLM or Triton, optimizing for both latency and cost, even for 70B parameter models. Let's define the scope. Functionally, we'll support text generation, code completion, and image generation. Non-functional requirements include low latency, sub 50 millibars P99, high throughput, 1,000 plus QPS, and high availability, 99%. Key clarifying questions. What model types will we support? What's the average input-output size? Do we need real-time streaming? We'll focus on text generation with an average sequence length of 256 tokens. We'll also need a rate limiter to prevent abuse, specifically using a token bucket algorithm to prevent bursts. The token bucket algorithm is preferred because it allows for some burstiness while still enforcing an average rate limit. We choose this over a fixed window because it handles sudden spikes in traffic more gracefully. Let's estimate our resource needs. With 1,000 QPS and an average request size of 1 MB, we need 1 GB of network bandwidth. Assuming each request requires 10 GB of GPU memory, and we want to support 10 concurrent requests per GPU, we need at least 100 GB of GPU memory. If we use 100 GPUs with 80 GB each, we'll need at least 2 GPUs. Storage, we need to store model weights, checkpoints, and logs. Let's allocate 1 TB per model. This is a starting point. We'll refine it with real-world data. We'll also need to consider the cost of data transfer between the CPU and GPU. This is a critical bottleneck because PCIe transfer speeds are much slower than GPU memory bandwidth. We can mitigate this by using techniques like CUDA-aware MPI to enable direct GPU to GPU communication. Here's the high-level architecture. We have separate read and write paths. For writes, model uploads, clients upload models to blob storage via a pre-signed URL. For reads, inference requests, clients hit a load balancer, which routes requests to API gateways. The API gateway then forwards the request to the model serving cluster. We use a cache, Redis, to reduce latency for frequently accessed models. Monitoring and rate limiting are essential side components. We use gRPC for internal communication because it's more efficient than REST, reducing serialization overhead and improving throughput. The API gateway handles authentication and authorization. Your interviewer is testing your knowledge here. Why not use a message queue like Kafka between the API gateway and model serving cluster? The reason is that Kafka adds latency, and we need low latency inference. We're aiming for sub 50 milliseconds latency, and Kafka would add tens of milliseconds. Let's dive into the core logic. We use a dynamic batching algorithm to maximize GPU utilization. Incoming requests are queued and batched together before being sent to the GPU. This increases throughput, but adds latency. The key is to find the optimal batch size. We use CUDA for GPU acceleration and TensorRT for model optimization. To ensure idempotency, we assign a unique ID to each request and track its status. If a request fails, we can retry it without side effects. Your interviewer is testing your understanding of batching. Why not use static batching instead? Dynamic batching adapts to varying request arrival rates, while static batching can lead to underutilization. A common mistake is to use a fixed batch size, which leads to suboptimal GPU utilization. We use a PID controller to dynamically adjust the batch size based on observed latency. The PID controller adjusts the batch size by monitoring the latency and adjusting the batch size to maintain a target latency. This is similar to how cruise control works in a car, maintaining a target speed despite changing conditions. For the data model, we use PostgreSQL to store model metadata, such as name, version, and location. We might be tempted to use a NoSQL database, but the relational structure of PostgreSQL provides better consistency and transaction support for metadata. We use blob storage like S3 to store the actual model weights. We index the model metadata table by model name and version for fast lookups. We use B-tree indexes because they are efficient for range queries, allowing us to quickly find models within a specific version range. A trade-off here is between storage cost and query performance. We considered using Bloom filters for faster lookups, but they have a risk of false positives. To scale the system, we use caching, replication, and sharding. We use Redis as a cache to store frequently accessed models. We replicate the model serving cluster across multiple availability zones for high availability. We shard the model serving cluster by model name to distribute the load. For static content, we use a CDN to reduce latency for users around the world. Remember the 1,000+ QPS we promised? Sharding is essential to achieve that throughput by distributing the load across multiple servers. We use consistent hashing for sharding because it minimizes data movement when nodes are added or removed. This is better than simple modulo hashing because it reduces the impact of node failures. An experienced interviewer will probe what happens at 10x scale. We'd need to evaluate the network bandwidth and potentially upgrade to faster interconnects like NVLink. We'd also need to consider using a distributed tracing system like Jaeger to identify bottlenecks. Furthermore, a rules engine becomes critical to manage complex routing and access control policies at scale. For fault tolerance, we use health checks to monitor the model serving cluster. If a server fails, we automatically remove it from the load balancer. We use leader election, RAF consensus, to ensure that only one server is responsible for managing the model cache. We monitor key metrics such as latency, throughput, and error rate. We set up alerts to notify us of any issues. If the cache goes down, we fall back to the model serving cluster, but latency increases. An experienced interviewer will probe what happens if the leader election fails. We have a backup leader election process to handle that scenario. We also use circuit breakers to prevent cascading failures. This prevents a single failing service from bringing down the entire system. We've designed a scalable and reliable AI model serving platform. The key trade-off is between latency and cost. Dynamic batching increases throughput, but adds latency. Caching reduces latency, but increases cost. A crucial component we discussed was the rate limiter, ensuring fair usage and preventing abuse. Next steps include implementing A/B testing, adding support for more model types, and optimizing GPU utilization. Remember our goal of sub-50 ms latency? Efficient batching and scheduling are crucial for achieving that in production and directly impact user experience, especially for those 70B parameter models.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.